The first speaker is Ulrike Neimeyer from the Max Planck Institute for Meteorology, and she will be speaking about tracer transport and how important are stratospheric dynamics and model configuration for stratospheric aerosol injection. So, please, welcome, Ulrike.
Yeah. Thank you very much. Yeah, I'm going to talk about tracer transport and how important this might be. I hope it will not be too specific. Many years ago, we realized, so I'm a modeler by heart and deeply into the geomip, and many years ago we realized that within our experience we do with the computer, when we inject sulfate into the stratosphere, that we destroy the so-called QBO, the quasi-biennial oscillation, which can be seen here. So it's an oscillation of easterly in blue and westerly in red winds that oscillate by roughly 2 years. It's within the tropical stratosphere in a small band between 20 or 15 or 10 to north and south. And when we inject sulfate up there, the sulfate is interacting with terrestrial and solar radiation, and it gets heated. So this layer then is warming, and this warming destroys this QBO, as can we see here quite nicely already in this transparency. So here we have two models. One is a WACAM and one is the ECAM. And we see that both models somehow disrupt this QBO, but they do it as a different amount of sulfate. One here needs 8 teragram of sulfate per year, and the other one needs 4 teragram. And we were asking ourselves, why? What is the question? And in order to make a long story short, I just show you the main results we got, which is now the vertical velocity. And this vertical velocity within this tropical area where this sulfate gets transported upward is different. It differs by up to 70% between the two models, and it's a lot stronger in this WACAM model than it is in ECAM. And as a consequence of this, we see that the transport there of these aerosols is very different. So we have in WACAM a much stronger confinement of our aerosols. They got up transported much more vertical up into higher levels than it is in this ECAM model. And as a consequence of this, or here, what I also realized is that when the difference between the model is also that we have a completely different horizontal resolution in our model. And my models, which is the ECAM, had a much coarser resolution. And when I created a finer, or used a finer grid, so a shorter distance between the grid points, then also my vertical velocity was increased. And therefore, I thought maybe this is also a matter of how I set up the model. The problem was that this ECAM was not really be able to run in even higher resolution, so I couldn't come close to the WACAM model. So I decided to take our newer model, which is ICON. You can see here the specific key of the model is that it has this triangular grid. So it's a non-hydrostatic model, and we can run this model with really, really different horizontal resolutions, from 160 kilometers between two grid points down to 2.5 kilometers. I use this broad coarse resolution here now. So I decided to introduce SF6 into my model as a tracer, and we can see here, so when SF6 is a gas, it's perfect for the industry. So it's colorless, odorless, non-flammable, non-toxic, so which makes it very, very perfect for the industry. But it is a very, very strong greenhouse gas. So 23,000 times greater global warming potential than CO2. But we also see that it really is, or here we have the concentrations and the growth rate. So it's constantly increasing in the atmosphere. But as it's more or less inert gas, it's a perfect tracer, almost perfect tracer for us, and has emissions close to the ground. So no? Yeah, no. So as it is an almost passive tracer, we introduce the emissions close to the ground. We use the EDGAR emissions inventory. And there are also a lot of data available. So it's measured by MIPA satellite data, by, for example, Gabi Stiller. And out of this is also age of air calculated. And I also use data of Helagani here to show the age of air. So why we could want to use age of air instead of S of 6 directly? As I said, it's a perfect tracer, but it's unfortunately not as perfect as if we wanted, because it has a sink in the mesosphere. And so for the age of air, there are data available where they try to correct for this sink, so that we now again can compare the model to the satellite data. And this gives us really the opportunity to see the transport in the model and to be a little bit more, to get more information. That's with a comparison with WECAM and ECAM, we have seen, okay, one model is faster, the other one is slower, but we don't know which model is right or which model is wrong or which is better or worse or however we may name it. So this allows us now really a comparison to our results. So here a little bit a word more about the circulation within the stratosphere. What we see here now is a Brewer-Dobson circulation. So the blue line is a tropopause, so all this is in the stratosphere. And here we have the tropical entry point of the SF6. So the SF6, as it gets transported within the troposphere, slowly goes up, and the main entry point to the stratosphere is the area within the tropics, and this is our entry point. And from here it gets transported within the Brewer-Dobson circulation, so partly up here within the tropical pipe. Here we see also the transport barriers, but also there's a deep branch where we have a much faster direct transport toward the poles. And this green line gives us a line of constant age of air, or the same age of air. So the age of air then, why do we not have all, okay, that's interesting. No, because there is half of the transparency missing. Sorry, we should see the explanation what we see here. So it's the age of air is, we calculate the age of air as the difference between the entry point and any point in the stratosphere. So the difference between these, the time it takes, so between these 2 points divided by this rate of entry. So we really have the age of transport here. And, but we see already that this all has the same age. So the transport up here is similarly fast as this transport to this point. This is now the SF6 concentration at this entry point in the measurements. All these here are measurements, and the blue line is my model result. So we see that this transport within the troposphere up into this to the entry point is quite nice. And here are the first results. We have satellite observations of the MIPAS data. Sorry, it really looks strange here. Maybe it looks better over there. It looks better here. So the age of air observation of the MIPAS data. And here, the age of air data of my model. So the model has 160 kilometers of the grid size. And so when we try compare it, so the brighter, the younger the air. So this is still in the tropopause, so below the entry point. So it's very young air, so the SF6 has just got emitted there. And up to here, we are almost more in the range of 6 years. So it takes 6 years for to come here, or 2 years for the tracer to come to this point from this entry point more or less here. So when we compare this now to this, or have a look here at the anomaly, which is a difference between the two, we see that overall I'm very happy with this. So it seems to be quite good. But the model is slightly faster. So the air within the model is a little bit younger. So we see, especially here in the tropical tropopause, that it's blue. So we have with this model here a little bit too strong upwards transport. This is the main transport region here. This seems to be quite okay. And then we have a very slow transport toward the poles. I must admit, I'm not really sure what's going on here. But overall, so we see the transport is slightly too fast, but not too bad. When we now change the resolution of the model, so we have here now observations, actually now 2 observations. This is another satellite, and we see immediately that also observations are not the truth, because the differences between these 2 products are even larger mostly than whatever we see between all the different model simulations. But this has much more sparse data. So I think this is a better product as we have a lot more data. So I think we can rely on this, and I use this for the comparison. And what I did here now is I changed the horizontal resolution of my model from 160 kilometer to 40 kilometer. And I also changed the amount of vertical levels, which is important in order to simulate this vertical transport on the QBO I've shown you in the beginning. If we have a not so good vertical resolution, the QBO is not coming up so well in the model. But what we can see here, when we increase the horizontal resolution, the shape is changing. So it's similarly more or less in the speed and the updraft, but we see that we get a different shape. So it's much wider here. And it's similar when we use here the lower vertical resolution. And especially here now, where we have a high horizontal resolution but a lower vertical resolution, we see that immediately this is really different now, that we have much older air and we have a much wider area where it seems to be transported upwards. So what's going on here? The answer is again given in the dynamics. So here we are back to the quasi-biennial oscillation, and we see for our 4 model simulation the results of this QBO. When we have the 160, so the low horizontal resolution, we see that we get this biennial oscillations quite well. This was, what's backward, this results here, which is from also when we calculate the differences, which is actually closest to the observation. When we increase the number of grid points to this 40 kilometer grid distance, then we see that here these westerly winds there don't come down anymore. We get here a layer of very strong easterly wind. And this layer of easterly wind blocks the transport of, so the QBO is generated by waves, it blocks the transport of the waves to higher levels, and so these easterly winds cannot come down anymore. And the same here for the lower vertical resolution, we get this layer of very strong easterly winds. And the transport in the tropics or out of the tropics depends on these winds in this QBO, because when we have westerly winds here in this level where we have our main aerosols, then we see, caused by the Coriolis force, we have the westerly jet, and we have somehow an inflow into the tropics. And we get, as a consequence of this, an updraft and a downdraft below this area. And it's the opposite when we have easterly winds. So when we have now the strong easterly jet there, instead of having an inflow into the tropics, we get this outflow out of the tropics. We have a stronger updraft here and a lower vertical updraft down there. And when we compare here now these two results again, which is on the left, the 160, so the best, and on the right is more or less the worst. So here we have this very strong easterlies. We can see just by, this is now the SF6 directly, we can see by the shape here how important this is. So we get here this updraft, and here we have more something that's gets something on the head, so that we don't have this, but we have a much stronger here transport meridionally. And when we look into the differences of our results here, we see that we are having differences in this area here now of up to 80%. Here we have 20–40% differences, which is when we think on solar radiation management and the transport of all our aerosols, and the huge differences we have between the results. It's quite important. So it shows us that it is important that we have somehow this good QBO, and it's not only the QBO here within it, also out of the tropics. So even when we would inject here around 30 south and north, we see that it would impact our transport in case the dynamics in the model are not correct enough. And just coming back now to the vertical velocity of the beginning, here we have these results I've shown you before, the two lines of Wackham and Eckham, and now I plotted the results of the icon model here, and we see that what I said, our model, the transport seems to be too fast, and it's faster than in the other two models, so we cannot really say now again, as we haven't done the comparison with SF6 here, we don't know which is really right, but I think we can conclude this is too fast, this is, I'm quite sure, is too slow, so maybe the Wackham or somewhere here in between we may have the right answer. And this is here now just the vertical velocity for my different cases, and showing that the blue line, so this line which is too fast, which was the best results, in the other cases is even faster. So again, showing it's important that we have a reasonable transport here. Yeah, and this is already, so as I said, it's important, we need the good dynamics in order to get good results for solar radiation management studies. So that after the distribution of our sulfate really depends on these dynamics we have in the models. And if we then have not a passive tracer as here, if we have sulfate, then we additionally get all this interaction with the transport, the concentration, stronger transport, stronger mixing, then we get at the end different particle sizes and so on. And also we see that it has influences on the tropical transport barriers, so how strongly will our aerosols be transported towards the pole. So the SF6 or Age of Air can really give us an answer how good our models are. So a step forward to what we do now. We only compare our model and say, yeah, it's maybe not perfect, but we don't know which one is right. Here we have a chance to really get a little bit more. However, ICON is a very new model. We still struggle a lot with this, as we have seen that surprisingly, only in the low resolution we get good results, not in the higher resolution. So there is something going on in the model which is not perfect, and we still, for myself, we work on this for since several months now to find out why we do get this strong easterly winds. We don't understand it. The dynamics in a model is very complicated. This model was done for weather forecast and tries to fit to this and not for the stratosphere, so we are quite sure we have some interactions we can't find. So it's a complicated business, but again, yeah, the good model dynamics are important. Thank you.
Thank you very much. Are there any questions? Yep, go ahead. Do we have a microphone?
Wait, it's easier.
My name is Ahmad from IPB University Indonesia. First, my question is related to your conclusion is there any, what do you think, is there any relation with the, you mentioned that the icon is non-hydrostatic, right?
It's very difficult to understand. There's a reflection. So
yeah, because
the icon is
in non-hydrostatic, you have more explicit vertical motion, right?
Yes.
And the QBO is more related to downward propagation. It means vertical.
Yeah.
Is it? Have you tried also to like making the icon is in hydrostatic? I mean.
No, we can't.
You can't.
No, we can't. So,
Okay.
No, that's not possible. So
Okay, that's one question, and the other thing is related to the how you define the deployment, the injection site, the start of the injection is whether it's because we have the QBO strong in the tropical, which part of the tropical that you start to deploy. I think because I'm not really know about how the modeler start the injection because it's really related to the dynamics, and if you different side of injection will also influence the result.
Yes.
Thank you.
Yeah, of course. So not for the SF6 here because this is emitted by industry. But of course, if we do solar radiation management, it's important where we inject. So I think at the moment we say we should maybe not inject within the tropics because of the problem also with the QBO, which is really important for the dynamics. Maybe we inject 30 north and south, but even then it's important that the model, which is our key working tool to understand what's going on. Even then, it's important that the dynamics in the stratosphere are good, that we really get a good distribution of the model. So of the aerosol, not of the model.
Thank you for a great talk. So we're pretty uncertain about how stratospheric circulation would change under SAI, if I understand, in large part because of a lack of observations of the stratospheric circulation through in situ tracers. So I'm wondering what sorts of in situ observations would allow us to have better model agreement or a better reflection of stratospheric circulation, and how would those in situ observations feed into this modeling research?
So what
in situ observations are needed, and how
yeah.
would they feed into the model?
Of course, observations are difficult. So here I used now satellite observations. I think this is the way to go. But we also may have LiDAR or balloon measurements, which are difficult to do and very expensive. Satellites, of course, as well. But I think so for solar radiation management, we still completely know this. So we are also working on a study now that we use model results to try to put it into a satellite retrieval to see at which point we may be able to see a cloud of injections, because we know that we can see it from a volcano. But a volcanic injection is like a huge amount within 1 hour, while solar radiation is a tiny little bit over a long, long, long time. And so it's much more difficult to be detected. And most probably they have to think about how to retrieve the data they have, but also maybe, do we need new instruments?
All right, thank you. There is another question.
Hello, I am Adolfo Luco from University of Mexico. Thank you very much for your talk. I have a question. Does ICON has the ability to reproduce interaction between the atmosphere, well, the troposphere and the stratosphere? And if it does, maybe when you reduce the dx from 160 to 40 kilometers, that may create smaller connections, or by vertical velocity fields, which may alter well, the SFD dynamics, for example?
I'm not sure I really get your question. So, interactions of...
Yes, like mass interaction between the stratosphere and the troposphere.
Okay,
Yeah.
yes. So, of course, it has the model. As I said, it's a model that's the core is really used for weather forecasts. So the German weather forecast is running more or less or a very similar version of this model. So it has all equations you need. It has tracers in for humidity, for example, and water and so on. And yes, of course, there is an interaction. So we transport upwards, but of course there's also a downward transport. Depending on, as I try to say, the model dynamics, they have to be good enough. In principle, the equations are there. It should be possible. So all could be perfect if a model with a grid distance of 160 kilometers needs to be tuned, and so you always have to skew somewhere to get your results into the direct direction. If this is done very properly, and if there is not something in the model, so it's really complicated. They try to damp, so they parameterize these waves on the one hand, then they damp them again, and so it's one layer above the others, and altogether it's then finally not working properly. But in principle, it should be able to do it.
Thank you very much.
Yeah.
Okay, thank you very much, Ulrika. And we move to the next presentation, which is going to be done by Sandro Vattioni from ETH Zurich, and addressing uncertainties of stratospheric aerosol injection of solid particles.
Thank you very much for the introduction, and thank you very much for having me here, give me the chance to present our research. The research presented here is from a consortium of many people, many different institutions, many people are involved. It's funded mainly by the Simons Simons Foundation. So I'm going to talk about addressing uncertainties of SAI of solid particles. So when we, why are we thinking of injecting solid particles? So the main research focus on SAI so far has been injection of SO2 due to the natural analog of volcanic eruptions. So most research has focused on SO2, but SO2 injections are subject to several limitations and adverse side effects, such as, for example, ozone depletion or stratospheric warming. It's probably among the more important limitations, stratospheric warming. Why is it important? Because it creates a circulation response. So what you can see here is the polar jet in the northern hemisphere, and it's rather straight here. And it can also be wobbly, like here. So this changes on an intra-annual basis or in a seasonal basis, and it determines the weather patterns over the northern hemisphere. So whether you have rain or cold air coming to a place, or warm air, so it determines the precipitation patterns and the weather patterns. And what is stratospheric warming doing now? Let's have a closer look. We again have the polar jet here, and if you warm the tropical stratosphere, you increase the temperature gradient between the polar region and the poles and the equator. And this strengthens the polar jet, and it also moves him northwards. And this results that in the polar jet be more straight instead of wobbling. So it has an effect on the precipitation, on the distribution of weather patterns and precipitation patterns in the northern hemisphere. So it's an adverse effect, and we have looked at this effect of SO2 injections. So we did two simulations: the SSP85 simulations and the SSP245 simulations, a rather moderate climate change scenario compared with a very strong climate change scenario, and you can see here the warming that would result as a difference of these scenarios in the troposphere. That's the climate change warming you see here. And that's the response of the zonal mean winds. And if we do now SAI to compensate the high climate change scenario to the low climate change scenario, you can see that the warming in the troposphere is gone now. And we have stratospheric heating due to the absorption of long-wave radiation of the aerosols. And we have big perturbations of the zonal winds in the stratosphere, which is what I explained previously. And when we look at the surface response of the temperature to SAI here, you can see that there are regionally or very big differences where regions are overcooled and other regions are undercooled. And so it's not a very equal distribution of the cooling effect. Now we did another simulation where we just switched off the absorption of the sulfuric acid aerosols. So the infrared absorption was switched off, and that's the result. So the warming is gone in the stratosphere, and we still have the cooling in the troposphere, and we don't perturb the winds in the stratosphere anymore. And also the effects at the surface, the temperature differences, or the cooling at the surface is distributed much more equally around the globe compared to when we have absorption of radiation, or when we have warming. So the heating is responsible for a big part of the dynamic feedback we see at the surface, and therefore we ask ourselves, are there better materials which could reduce stratospheric heating? And the short answer is yes, there is. So we did test some materials with our aerosol chemistry climate model. We injected 5 megatons per year of materials in the stratosphere, and you can see that many materials such as diamond, silicium carbide, they result in larger radiative forcing compared to SO2 here. And most importantly, calcite and diamond here, they also result in significantly reduced stratospheric heating. Here, stratospheric heating as a function of altitude, it's significantly reduced compared to SO2 injections. So there is potential for alternative materials, but the results presented here are subject to substantial uncertainty. So this is the model we used. It's the solid particle microphysics scheme we implemented in our model. It accounts for coagulation of the particles, deposition, sedimentation, deposition in the troposphere, interactions with radiation, and also heterogeneous chemistry. And you can also model the feedbacks between these different processes in the model. So that's everything very nice, but very little is known about these processes in the stratosphere, because solid particles do not occur in the stratosphere naturally, other than sulfuric acid aerosols. So we need to make a lot of assumptions to represent these processes in our model. And that's basically what we did to the last 4 or 5 years of research. We tried to address these uncertainties of all these processes to get a better understanding of the risks and benefits of solid particles, of solid particle SAI. So we mainly looked at alumina and calcite particles because there some of the physiochemical properties are already known. And we wanted to quantify the ozone response compared to a sulfur injection, their warming, and also the radiative balance compared to sulfur injections. And we did this by first going into the lab. So we did experimental research where we looked at the nanoscale. So how do solid particles interact with trace gases in the stratosphere? How do they coagulate with each other, etc. And then we implemented this in our Earth system model, these processes, and tried to quantify the downstream impacts of solid particle SAI. So let's first give a brief overview about the heterogeneous chemistry of calcite particles, so how calcite particles interact with trace gases in the stratosphere. calcite is a base, so it reacts with acids in the stratosphere. So it's mainly H2SO4, HCl, HNO3. So the first two here, they are present in the parts per billion range. So they are probably the most important one. So HCl is the reservoir species of chlorofluorocarbons, which are responsible for the ozone hole, which is occurring every year over Antarctica. So if we would take up HCl on the particle surface and form these salts, chlorine would be removed from the stratosphere via the sedimenting particles. So we would have the co-benefit, win-win situation of having more ozone, healing our ozone layer, and cooling the global climate. However, there is also HNO3 in the stratosphere at even higher concentrations. And if we remove HNO3 from the stratosphere via the similar process, we reduce the NOx concentration and we reduce the deactivation of active chlorine in the stratosphere, which would lead to ozone depletion. So the question is now, which process dominates? And we have looked at literature values, and they're all across the scales. So they range about many more orders of magnitudes, and they're measured at different conditions: room temperature, colder temperatures, relative humidity, etc. So very difficult to make sense of it. So we need measurements at real stratospheric conditions. We need to quantify the uptake coefficient. So the uptake coefficient is the fraction of molecules which result in uptake or reaction upon coalition. Yes. And so we need to quantify this under stratospheric conditions. Because there might be also a passivation effect, so you could have very strong uptake in the beginning on calcite surface, which is still fresh. And if the surface saturates here, as you can see here, if the first layers of the products form, this could passivate the interior from further reaction. It could seal it off. And the uptake coefficient could go down with time. And so we did these measurements. I don't want to go into the details of these measurements. I just show the final results. Our measurements are shown in green here, ERA and XPS, and these are other measurements from other previous studies. And we plot the uptake coefficient as a function of the exposure. The exposure is the concentration of HNO3 and HCl applied in the experiments, multiplied with the time of the experiment. And there is a picture evolving when you look at this. So if at the beginning, with only small exposure, you have very high uptake coefficient, but the longer it takes, the larger the exposure is, or the longer the particles are in the stratosphere, the smaller the exposure gets. So if you arrive at typical exposures of a particle injected into the stratosphere for SAI, we are at around these exposures for these two species. And so you can look up the value, which results here. It's about 10 to the minus 5 to 10 to the minus 4 for HCl. So it's a rather low uptake coefficient, which would result if you integrate the uptake over stratospheric residence times of the particles. And so we took these values, 10 to the minus 5 and 10 to the minus 4, and put that into our aerosol chemistry climate model to simulate the effect. Okay, I also have some problems with the representation of the slides, as Ulrike had. It shouldn't be the case, but so you almost see no difference for this most likely scenario with these uptake coefficients. It's almost not doing anything to the zonal mean ozone column, so a zonal mean ozone column difference. And I also plotted SO2 as a comparison, and you can see the ozone depletion would be substantially larger. And however, there is considerable uncertainty on these results here. It's just taken from a few measurements. If we go to the largest possible uptake coefficient of about 10 to the minus 3, before you get passivation, we also simulated this case for HCl. So if you have very strong uptake of HCl, here 10 to the minus 3, you get a very efficient healing of the stratospheric ozone of the ozone hole over Antarctica in the annual mean. You can see that here, it goes up. However, if you apply that 10 to the -3 uptake coefficient to HNO3, you really decrease the deactivation of chlorine, and you get ozone depletion of up to 10%. So that's the most likely scenario here around 0. These effects would likely cancel each other out. But yeah, there's considerable uncertainty beyond this, but the most likely scenario points rather to not a big impact. We can do a similar analysis for alumina particle injection. So alumina is not a base, so it does not interact with the gases in the stratosphere, or not. It's not in the way that calcite does. So the bulk is like chemical inert to changes, but it can anyway take up, for example, a coating of sulfuric acid at the surface. But the sulfuric acid will most likely contract because it has a rather steep contact angle, which leaves free surface of alumina for heterogeneous reactions. For example, chlorine nitrate plus HCl. And this reaction was measured previously by Molina et al. Almost 30 years ago. They came up with an uptake coefficient of about 10 to the -7. They did this research for the purpose of space shuttle exhaust, which also contains alumina particles. But they applied higher HCl concentrations in their experiments because space shuttles also inject HCl. So to a normal background stratosphere, you would need to extrapolate these values, the measurement values here by Molina, to the stratospheric concentrations of HCl. We did that by applying a Langmuir-Hinchelbutt parametrization of reaction and absorption. And there you get, again, a very big spread of possible outcomes. So the uptake coefficient could be as high as almost 0.02, but also as low as almost 0. And more realistic is rather the lower scenarios, because HCl will likely dissociate at the surface, and there will also be HNO3, which will co-adsorb at the surface at even larger quantities, and that will displace some HCl from the surface, which efficiently would lower the uptake of these species at the surface. So the most likely scenario is also rather at the 0 line here, but we can't exclude this strong ozone depletion scenario up here. So we need also more research to quantify this better. So to give a summary at the end, for 1 watt per square meter of radiative forcing with our model, we need more material for alumina and calcite to be injected, because the particles are heavier, and the residence time of the particles in the stratosphere is much smaller compared to the sulfuric acid aerosols. But you would, for the same radiative forcing, you would need only a smaller burden. And at the top, and the most distinguished benefit is the stratospheric heating, the reduced stratospheric heating of especially calcite particles here. And the ozone response here, I show it again. For SO2, the uncertainty is much smaller. We know much more what we get, but it's likely larger compared to the total ozone. The most realistic scenario is likely resulting in larger ozone depletion compared to alumina and calcite. But for the solid particles, we have much higher uncertainty. So there's more research we need to do. And these model results are also subject to structural uncertainty, or to further uncertainty, which I want to point at in the following 2 slides. It's important to note that we inject our particles in our climate model grid, which has a resolution of 1.5 kilometers times 320 times 320 kilometers. So it's a very, very large grid, and the particles are equally distributed in that grid. so we do not account for plume processes. So upon injection of the particles might coagulate with each other, form clusters, etc. These processes are all not accounted for, and this will likely change the scattering efficiency of the particles and also the sedimentation velocity. Because what we figured out, or what we found, is that if you look at the integrated lifetime of a particle in the stratosphere, compared with the agglomerates of these particles, so it's a monomer or 2-mer or 4-mer, it substantially goes down. So if you have agglomerates instead of monomers, you decrease the efficiency. And what we assumed is that we inject spherical monomers. And also the interactions with clouds, with, for example, cirrus clouds, is not accounted for in our model. And this could add another radiative, positive or negative radiative forcing. So it could, because the cirrus clouds warm the climate, so if you would form additional cirrus clouds, you would decrease the cooling efficiency of solid particles. And so we looked, because the scattering or the coagulation of these particles is so important, we looked at what would be the optimal size or the optimal agglomerate size with the highest scattering efficiency. We used the multi-sphere T-matrix code and looked at the integrated upscatter cross-section, so in annual mean in the tropics of particles. So these are monomers here with different radius, and these are the number of primary particles per, in an agglomerate. So this is a 1-mer, a 2-mer, a 4-mer. Here we have a 32-mer. This could look like this, so a monomer with a particle consisting of 32 single monomers. And these particles would likely form if you inject them from an aircraft. And the strongest the strongest scattering efficiency you get from 0.16 micrometer radius, and if you go larger and lower, you decrease in scattering efficiency, and also with increasing agglomerate size, you decrease the efficiency. If you look also at the stratospheric residence time of these particles, it obviously decreases with increasing radius and with increasing agglomerate size. And so this needs also to be counted in. And if you now combine these two effects, this is the resulting picture. So this is the residence time integrated refractive solar energy per aerosol mass of like a particle of this size or an agglomerate of this size of monomer particles. So this is kind of the optimal size. But when you're beyond this or below this, you get a significantly smaller scattering efficiency, and you decrease the efficiency. And we then went to the lab to look at coagulation of particles. So we used the tank, a 3 cubic meter aerosol tank, and filled it during 6 hours with 210 nanometer calcite particles. And we observed how the coagulation evolves over 3 days. And you can see here with a stippled line the experimental results, and the solid lines are modeled, but the model does not account for coagulation. So the difference between the model and the experiment is due to coagulation. So the decrease in overall overall concentration is due to sedimentation and wall losses. So with every day you have like wall losses and sedimentation, you decrease, but you also have coagulation, which moves the particles to larger numbers. And so from day 0 to day 3. And what we observe is that coagulation mainly happens during the first day, then probably concentration gets too low. We didn't find dependence on like turbulence. Turbulence likely have not an effect, but there is a trade-off between the narrowness of the size distribution and the concentration. So the narrower the concentration, you make your size distribution, the lower the concentration, because you select more particles away. So you can see here is a very broad size distribution and not monodisperse as in our model, idealized. So it's rather larger, and we also see coagulation, and this could decrease the scattering efficiency in the end. And we also saw by optical analysis of the particles that the particles are also not spheres, they're like aspherical, and they are already agglomerated upon injection. And that's a problem which needs to be addressed, because the fuel to payload ratio of an airplane, when you inject particles with an aircraft, the fuel to payload ratio increases exponentially with height and flight time. And for SO2 injection, it's very easy. It's a compressed gas. You can compress it for transport, and you can release it relatively fast. You just open your valve, and you forget about the gas, because aerosols are only formed about 30 days downstream. But that's not the case for calcite or for solid particles. They must be dispersed upon injection. And that's a problem. So it takes much longer to disperse them. You can't just dump 20 tons of solid particles from an airplane in once, because they would fall from sky like stones. So you need to do it slowly, and so you would likely need many more airplanes compared to SO2. And you probably also require a carrier gas or a carrier liquid. So to sum up, there are many promising advantages of solid particles over SO2 injections, but there are also significant uncertainty on their optical property, on the physical and chemical properties, and also on how to disperse these particles in the stratosphere, and how do they coagulate, how can this be controlled. But given the big potential, I suggest it's high time to conduct the research to reduce these uncertainties, because not doing so could also mean that we stay locked in a second best option with SO2, and that at some point in the future realize, okay, solid particle work much better, and we need to do the whole assessment of SAI again. It could also result in false conclusions. So it's really important to build up model capabilities and do the experimental work on solid particle SAI. Thank you very much. Yeah.
Well, we're going to go for only maybe one question.
Yeah, that was a very interesting and visually appealing talk. Thanks a lot for that. I was just wondering, because you're injecting particles, so it's like if you're considering the ozone depletion, the UVA and UVB spectrum from the solar radiation is going to be affected. But now that the ozone is sort of being restored with calcite injection, I was just wondering what is going to be that, what's the effect of that injection going to be on the rest of the spectrum, that is the visible and even near infrared? Have you looked into that?
Mm-hmm. So what the effect of injections are on the UVB, on the UV?
Not just UV, but the entire solar spectrum.
Of
because
the
particles
entire solar. Yeah, so you mainly scatter the radiation, but it's scattered in all directions. You want to have as much as backward scattering as possible. That's why it's important to have the right size of particles, because if you have too small sizes or too large sizes, you might have more forward scattering than backward scattering, which does not help. So you want to have backward scattering. And so therefore you need to have the right particle size, and also the agglomerates. Agglomerates have more forward scattering than backward scattering, so you want to avoid the agglomerates. And that's why it's very important to have the size of the particles correct. Yeah.
All right. Yeah. Thanks.
Sorry, we need to continue. Yeah. Thank you very much. The last talk is impacts of stratospheric aerosol injection on concentrations of tropospheric aerosols and implications. A study based on CSM2 and geoschem with advanced particle microphysics, presented by Van Chen Yu from University of Albany.
Thank you. So actually, the title you give is the older one, but in the agenda, we have updated the title. So I will talk more on the efficacy. So my name is again Feng-Chun Yu. I'm Yu Albany. So today I will share the insights based on 3 model. So I again slightly modify the title as shown in the agenda. Instead of based on 2 model, we have 3 model. 3 global model, CESM2, welcome of NCAR, Geoscam, and also E3SM of US Department of Energy. All these models with a sectional size resolver particle microphysics. We call that model is APM. And the key message of my talk, based on these studies, we find much high efficacy of SO2 and sulfur acid SAI compared to the previous results. So what is the SAI efficacy? So basically it's defined as the short wave radiative forcing per rate of injections. So the unit is watt per square meter per injection rate. And we compiled this previous study for the 2 materials. One is SO2, another is sulfur acid particles. And you see the efficacy usually is around -0.2 to -0.8 watt per square meter per telegram sulfur per year. And that sulfur acid injections is slightly more high efficacy. People have been used that to estimate the cost of the deployment. I give 2 examples here. Smith and Wagner use next 0.25 for their estimations. And late, they use another estimations. Smith use about the next 0.6. So this efficacy really decide in order to get the cooling, what's the amount of the stuff you need to carry over. So from these results, you can see there are large uncertainty in the model similar to SAI efficacy. And that's important. Actually, the National Academy of Science, Engineering, and Medicine published this report, and they emphasize the need to reduce uncertainty. And I give 2 quotes here. One is the overall magnitude and the spatial distribution of the forcing you get from the SAI depends strongly on the particle size distributions. Another point is one of the research priorities for the SAI is thus to address critical gaps in knowledge about the evolution of the aerosol particle size distributions. So particle size is very important, and we need to understand that. So how we deal with the particle size distributions? So we developed this called APM model. It's a sectional model. And we started, actually I developed this model during my PhD work with Richard Turco during the, about 1998, looking in the particle formation and control formation in aircraft wake. If you can click the movie. So in the past several decades, there are a lot of studies try to understand how particles form and control form in the aircraft exhaust. So what this video show, you have the kind of seeding aircraft, and you have another chasing aircraft to get in the plume and make the measurement. And if you get in the plume, you see a lot of particles appear. So that's in the aviation industry, they are very interested in trying to figure out what controls these particles. So we developed this model and try to explain and predict the particle formations. So several key findings based on our past study. We found that the chemical ions, sulfur acid, and organics are really important for volatile particle formations in this exhaust. And also, we found that the coagulation is also very important as these particles evolve in the expanding plume. And we found that the volatile particle formed in the exhaust from the chemical ion, sulfur acid, and organics can contribute to the chemtrails. So these are the key findings we published a while ago. Now we use this model to look into different things. So in the literature, you probably see two versions of the model. We call it the comprehensive APM and the simplified APM. So the comprehensive APM is for the detailed process study, especially for the plume scale, okay? So we have actually used this model for the SAM plume process. We published a paper last year to look in the new particle formations. So the nucleation pathway and the particle size distribution evolutions in aircraft plume with the sulfur acid SAI. And we can simulate the particle formation and evolutions. And we find that injecting the sulfur acid, you can form a particle of the right size and very narrow due to nucleation and coagulation growth. We have also looked into the control mitigations use this plume scale model. We published another paper looking at the primary solid particle contributions and also the volatile particle contribution to the control formations. So we use this model for the control mitigations. We collaborate very closely with the aviation industry. So currently, actually, we have two separate projects funded by GE Aerospace to look into the control mitigations. So that's a plume model. We also have a simplified APM section model for the three-dimensional models. And that model have detailed process. I do not have time getting the detail, but we separated particles of surface, second particles from the prime particles, like black carbon, organic carbon, sea salt, and dust. All have different sectional, have different size range. And we consider the detailed microphysics, nucleations, condensations, coagulations, aerosol interaction, and also depositions. So this interaction, we also consider coating of the primary particles due to the condensation and coagulation process. So we first put the model in the GeoScam and the WolfCam, and then last couple of years, we put the APM into the CSM2 and also the Wolf CMAC in collaboration with the US EPA. And in collaboration with the DOE Lawrence Livermore National Lab, we put the aerosol in E3SM. So information about this paper can found in the publication of my webpage. So below, I will show some example about three-dimensional modeling. Before going that, at some point we think, and as pointed out in the previous talk, the plume scale process and the three-dimensional process somehow should be integrated. So one of the part of the future work, we want to develop parameterizations based on this plume scale process and parameterize that in the three-dimensional model for the SMA studies. So based on same model, but different applications. So for the three-dimensional model, many of you know, it's basically we divide the atmosphere in the grid box. So you have the horizontal grid and the vertical grid. In each columns, you have all the physical process, cloud, radiations. So what we did is we added the APM size resolved microphysics in this three-dimensional model and look at each like the box model and look at the process. So we, of course, put a model, we can simulate the particle microphysics. We compare the microphysics with different observations. So here, give one example based on GeoScam simulations. We run the global model for more than 3 decades, and for the background without SAI, but including volcano. And we try to see how model captures the variation of the aerosol in the stratosphere. So what's shown here is the model simulate particle size distributions and also the particle properties and compare with some of the measurement. So the upper panel shows the particle size distributions. That's the time, yield, size, and the color show the size distributions. You immediately notice a spike. And what's shown is one grid box, 17 kilometers above the surface. So it's in stratosphere. The site location is Laramie, Wyoming, where we have long-term balloon-borne measurement. And we try to compare with that. So size distributions, based on size distribution, we can calculate optical properties and particle of different size cutoff. So the optical properties, that's the stratosphere aerosol optic depth. The symbol, black one, is the global GLOSAC satellite observations. The red line is the model simulation. So you see the model captures these kind of variations and a volcano. We also compare with the balloon-borne aerosol measurement of different cutoff size. You'll see the model captures the variations. They are different in some details. So the model reasonably reproduces the observations. And we also, other model, E3SM and CSM, we have similar kind of performance. So now we use the model to do the SAI. We have 3 different models with different dynamics, different chemistry, and different resolutions. And we do the SAI scenario is we use regional injections, 30-degree south and 30-degree north, all longitude 90 and 21 kilometer kind of injections. We use the instantaneous dispersion in the grid box. So subgrid plume process is not considered yet. We consider 2 materials, SO2 gas and also sulfur acid particles. For the particle, we assume a log normal distribution with median July diameter of 300 nanometer. And we see how model will show the efficacy. So this figure gives you the information what we simulate. So first we run for the model for all 3 models for the 5 years. What is shown here, let's explain the particle size distribution evolution. So upper panel is for the SO2 injections. Lower panel is the sulfur acid injections. For the 2 sides, we select the 2 sides to show how the size evolve. So for the SO2 injection at this point and this mid-latitude, you see the different evolution of particle size distributions. You'll see a lot of nucleations due to sulfur acid. Mid-latitude, not in the location of direct injections, but you still did get a nucleation due to transport. And the particle size distribution usually is more spread. If you're injecting particle of the 300 nanometer log normal, they maintain this log normal. So you'll see the difference in the size distributions. And that show up in the particle mass. We use the same 10 telegram sulfur per year of injection rate. And you'll see the burden of sulfur are different. You get a high concentrations, use the sulfur acid because they're small, their deposition rate is slower. You'll see the size also different. SO2 injection, you get a large size. And the extinction coefficients also different because of difference in the mass and also their size. So sulfur acid get a more extinction coefficient, a high extinction coefficient. And that will reflect in the radiative forcing. So what's shown here is a 3 model. Radiative forcing, E3SM, CSM, and GeoScan. SO2 injection, sulfur acid injection. Again, the example shown here is 10 telegram sulfur per year. So you'll see the cooling effect of the short wave solar radiations. So the model, similar magnitude, but different in the spatial variations. Sulfur acid injection, much strong cooler effect, and also have different in the spatial variation, but it's similar. How these compare with previous model estimations? And that's we show here. Again, we already show that these are the previous model simulation based on SO2 and the sulfur acid injections. If we add our 3 model, all based on sectional model, you immediately see the difference. Again, so This solid symbol point is based on 3 different APM models. This model has a difference, but they are similarity. So kind of quickly summarize what we found out based on this comparison of the SAR efficacy. So again, efficacy is the radial forcing per injection rate. We find first, the APM-based have high efficacy. And that efficacy is, especially for low injection rate, it's a factor of 2 to 3 more efficacy than the previous model simulations, and both SO2 and sulfur acid. Another point is we find we are steep in decreasing in the efficacy. So you see in the previous model, you see some decreasing, but based on APM, it's much steeper as we injection rate increasing. And the efficacy of SO2 SAI compared to SO2, the ratio is higher than the previous model. So previous model sees a high efficacy, but the difference is not that huge. Based on our model, the ratio is about 1.6 to 1.7. So you see the much high efficacy of the sulfur acid. So these are our new kind of insight based on our model. So what's the implication of this finding? And that's my last slide. So first, we need to figure out what's the reason of the difference. Because we know the efficacy is really important. It's really control what's the cost, and also what's the side effect. So because the amount of the stuff you put in the stratosphere affects their side effect. So for that, we need a detailed model inter comparisons, try to understand why it's different. And we have a GeoMIP Friday, and I think we will have more discussion there. It remains to be established which model gives more realistic results. So we are not assuming which model is more accurate, we don't know. But our APM model shows high efficacy. In order to do that, we need a suitable measurement. Measurement needed to constrain the model and also needed to reduce the uncertainty, and also test the different models, see which model give more realistic kind of predictions. If our APM model is more realistic, then we have some implications, and we needed to find out if that's true. So we may not need as much amount of the injection in order to get the desired cooling, and which will, again, will reduce the cost and side effect. If the APM base is right, then the sulfur acid SAI may be more cost effective than the SO2 because their ratio is large enough. We all know that sulfur acid gas and SO2, their weight are different, but the ratio is higher than that. So that's also important. And we show a steep decreasing. And that's also have implications because a lot of the future, if we do the field measurement, but probably it's small scale. Small scale results could be different compared to large scale. And we need to keep in mind about that when we do the scale up of the results. So that's all I prepared. And thank you for your attention. And I'll be happy to answer any question you may have.
Thank you very much. Very interesting. Is there any question? Yeah, go ahead.
Hi. So I have 2 questions. One is, like in the last few slides, you showed that there is a general decrease trend when you increase the, I guess the particle rate, size, or rate, right? Yeah, right, this one. Can you elaborate a little bit more why you have less, fewer net UA shortwave efficacy as you increase the rate? That's the first one. And the second one is, I'm just curious, are there any plans you're gonna take to evaluate your model results? which is quite different from the previous ones, right?
Yeah,
Thanks.
thank you for your questions. So first question is why our model show kind of decreasing as you injection more. So that, again, that's the efficacy is normalized per injection rate. So the reason is when you injection more, the particle getting big, and you have more concentrations. When you're getting particle getting bigger and they're large, they are bigger, they fall down, their lifetime reduced. So their efficacy reducing per injection rate. So basically, it's because of difference in the particle size distributions. The more stuff is there, the particle getting bigger, and their lifetime reduced. And that's see the decreasing. Your second question about the validations, I think it's very important. For the SAI, we do not have measurement yet. So only validation we have probably the volcano. So we want to use a volcano to see how model doing. But we also need to be cautious. Volcano is different from SAI. Volcano, basically, you're injecting stuff just very quickly in a very short time. SAI, you do very slowly, globally. So we keep that in mind. Things could be different. But as I showed in a previous slide, we do compare with the volcano. And our model seems able to capture the variation of the particle size distribution AOD. So I think the best we can do now is the volcano validation. But for SIM, hopefully in the future we will have more measurements become available.
Thank you very much. Please, let's thank all speakers for this exciting, very intimate session.
Thank you.